I guess we can start now. So hello again, everyone. Today's lecture, I'll be talking about two things. So how we can instruct LLMs to be more aligned with human preferences. And for the later half of the lecture, I will talk about how we can extend their capabilities by augmenting them with tools and external knowledge bases. So by now, we're all very familiar with the powers and wonders of LLMs and how pervasive they have become in our daily lives. Mostly, their widespread usage is their capabilities in generating and handling tasks from prompts from a diverse range of tasks. And the fact that these responses are human value aligned, we actually found their responses pretty useful, as opposed to non-aligned responses from models like GPT-2 or like Pegasus. So pre-LLM era models. And because of this usefulness, a lot of companies, like search engine companies like Microsoft, Bing, and Google, they try to incorporate LLMs in their search engine results, in addition to their standard retrieval results. And because of the training data sets contain text from different languages and images, well, actually multimodal needs extra alignments, but as long as the multilingual is concerned, the LLM can handle multiple languages as well, to some extent. And of course, we'll be talking about it later, but we can extend the capabilities by incorporating external tools and knowledge bases before generating the response. And depending on how cleverly you prompt these models and how you integrate past history of conversations, you can think of them as an agent. You can think of them as an autonomous agent where you give LLMs a high-level task and just let it figure out the sub-steps, intermediate steps to achieve the goal. Or you can think of them as social agents where you give kind of slightly different personas or personalities to each LLMs and have them interact with each other. So this has been quite popular among researchers from social science or psychology or cognitive science domains. Okay, so let's briefly overview how ChatGPTs are trained. So we start off by collecting a data set, as with all other ML tasks. And we call this demonstration data because we are using human labelers or human annotators to demonstrate the intended or desired behavior or the responses regarding the corresponding prompt input here. So from large prompt data sets, we sample a couple of prompts that we think are important, and then we recruit human labelers to generate responses for these particular prompts. And then it's just standard supervised fine-tuning from there. We'll take a look at this step in more detail. And this particular step one is called instruction tuning. But conceptually, this is just exactly the same as supervised fine-tuning, right? Because you have the input data and you have the output data, which are both in sequences. And you just fine-tune on these input and output pairs. So this is an example where we query ChatGPT to generate or explain reinforcement learning to a 6-year-old. And then it generates the answer or the explanations using simple English terms. So, it's kind of working. And another example where we ask the same thing, but this time we want the model to generate, not this one. Yeah, we want the model to generate response tailored to a CS undergrad, for example. And this time the response is more involved in the sense that it uses, computer science related terms and whatnot. Okay. So step one can be sufficient, but in some scenarios, we need some additional alignment. For example, depending on the quality of demonstration data, the intended output or the generated output may not be good. In that case, we need step 2. Or we can imagine scenarios where we want to further align the responses to a specific group of people. Or go ahead.
Are these data labeled by humans, right? Or are they
Yes, we'll get to that in a second, but essentially they are labeled by humans, yes. Yeah. So the second scenario is where you want to tailor your LLMs to your internal, like company policy or whatever. Then you need some sort of more tailored response, right? So that's when this step 2 can be applied. So for step 2, given that we already have this instruction-tuned model, we ask LLMs to generate multiple responses for a given prompt. And again, we recruit humans or the actual users to rate these responses or rank these responses. Yeah, so now that we have some sort of scores or the rankings of these 4 responses, we are going to take the original LLM's model and then make it generate either the scores or the rankings of these responses. So in the original paper, these 2 SFT and RM real models are actually the same LLM that generates it. Yeah, and this step is called this thing is called preference modeling, and the outcome that we have at the end of step 2 is the reward model that takes the responses and generates the scores or the level of preference. Okay, and going back to your question, so how do we actually gather these reward or preferences? So we can already think of this kind of naturally occurring preferences in our daily lives, right? For example, this Stack Overflow post, original post asks a question, and a couple of the members from the community generates or creates an answers, right? And these answers are either upvoted or downvoted, and these upvotes or downvotes naturally hints the preference for this preference among these responses. So these scores can be considered as preference. So in this case, answer A, the answer above is better than answer B. And in case we don't have this kind of data set, we can also collect distance signals. So in ChatGPT, you probably noticed this regenerate button, right? So this is where we usually click this button when we are not satisfied with the initial generation. So there's an assumption here that when the user clicked this button like multiple times, the previous generations are most likely not satisfactory, right? And the final sort of generations that user chose at the end should be the most preferred response. But of course, this is a distance supervision. It may not be accurate. But the fact that millions of people use this every day, so in terms of scale of this kind of distance signals, it can be useful as well. Just because of the fact that we have so many of them, they can be used in learning. Yeah, so click this generate, and then it will regenerate the response. And of course, we can, spend some money and recruit human laborers again to gather the explicit preference data. So given these 4 responses for this particular prompt, we're recruiting the human annotators and ask them to rank this in terms of their preference. And then these data can be used to train this reward model. Okay, so now that we have the reward model, so how do we actually use it to further align our instruction-tuned model? So we use this technique called reinforcement learning. So it basically corresponds to learning this policy, or the policy in our context is whether to generate this token over the other token or not. And then based on the generation, the reward model will compute some sort of score, positive, negative, or whatever, and then this score will be fed back into the original instruction tuned model to update their policy in choosing the next token. And the reward is given not every step by the generation, but it's given after the completion of the generation, right? So in this setting is related to the reinforcement setting where you get the reward in a delayed after a delayed amount of time. So OpenAI people call this reinforcement learning with human feedback, RLHF for short. And in the field, there are some other ways to align these language models. One that's mostly used is called direct preference optimization, and in that approach, it get rid of this RM model, and instead we just need a paired response, a good response and a bad response for a single prompt. And then you can just directly optimize this from those paired responses. Yeah, but ChatGPT is trained with RLHF. That's what they say. Okay, so we've been talking about alignment, and what does this actually mean? So, the language models, they're trained to optimize certain objective function, right? Mainly or predominantly the next token prediction task. And doing well on that task is not necessarily the same as producing outputs that we want, right? So the alignment concept is related to what we actually want the model to do, whereas the capability is evaluated by how well it is able to optimize the objective function. So yeah, those are the sort of two different concepts there. And the fact that the language model is trained on the next token or mask token prediction task, and also the fact that we want our language models to be more helpful, don't produce less hallucinations, produce results that are interpretable, and also generations that are not biased. So these are the things that we want from the models, and the fact that it's trained in this manner results in some sort of discrepancy between what we want and what they actually do well on. So the task of alignment is actually reducing this gap between these two phenomena. And we have just seen that RLHF is one of the ways to reduce these gaps. So we are bringing the language models closer to the center point, assuming that the center point is where we want to head to. Okay, so these are sort of the basic overview of how ChatGPT has been trained. And next, we will take a look more closely on the step one, the instruction tuning part, because this is the first breakthrough that achieved the level of ChatGPT. So again, consider non-aligned LLMs, and we ask questions like this. This is actually the output from GPT-3. So when we ask questions like explaining moon landing to a 6-year-old, it just generates more questions, like similar questions, because the model has been trained on large data, and some of the data might have contained like trivia questions. So generating more questions are perfectly plausible generations as far as the next token prediction task is concerned. But this is not actually what we want, right? We want the generations to be actually the answers to those questions, right? Something like this. And yeah, so how do we actually do that? It's pretty straightforward. You can just fine tune it with the responses that we want, right? So that was the step one. So if we briefly recap the pre-train fine-tune paradigm, so ever since the transform models were published in 2017 and the corresponding BERT models were published, in NLP, people have been just following this pre-train and fine-tune paradigm where you just train this either BERT model or ROBOTA model on like really large amount of corpus following the next token prediction task with the mass modeling, language modeling. And then you take those pre-trained model and just fine-tune it on your data set of interest. So because this data set is often, because the task is often, single task, the number of labels you need to consider are pretty small. For a sentiment classification, it's just either positive or negative. So this process, this approach is very, very effective and very, very simple, efficient. So when we are trying to do the instruction tuning, we just take this approach and scale it up to fine-tune on as many tasks as possible, right? So not just on the sentiment classification task, but also reading comprehension task, natural language inference task, etc. So now we will be fine-tuning on diverse set of tasks. So the number of labels to consider are a lot more than the standard fine-tuning. But essentially the idea or the approach is the same, right? It's just pre-train and then fine-tuning. So how do we actually leverage the existing NLP data sets? In step one, we said that humans are recruited to produce these kind of data sets, right? But we can also make use of the existing NLP downstream data sets. So we could have a data set that asks for the boiling point of nitrogen. Another data set can ask language model to do some arithmetic computations and so on. So we collect a bunch of data and then we append instructions to each input. So instruction here is what we want the language models to do. So please answer the following question could be an instruction. Answer the following question by reasoning step by step is another instructions. And the input in this case is the actual, the question themselves. So yeah, and then we have the corresponding output paired with the instruction and input pair. So conceptually, this instruction and inputs, these two tuples are, as far as the language model is concerned, are just inputs, right? But we just separate them when we are preparing the data sets. And the idea here is that when these language models are trained on these many data sets, it is able to perform or generate appropriate responses to unseen data sets as well. Yeah, so the main difference between instruction tuning and standard fine-tuning, conceptually, they're the same, but the difference lies in how we prepare the data samples, especially the input portion of the data. So standard fine-tuning trains model on input examples and corresponding outputs, but instruction fine-tuning augments the input-output examples with the instructions to perform each specific tasks. And let's see how we can do that. Okay, but before that, so these are sort of the initial list of NLP tasks that were considered in the first paper that proposed instruction tuning. So we have 62 NLP tasks where they can be categorized into 12 task clusters. So we have natural language inference, common sense reasoning, all sorts of different tasks. Okay, so now let's look at how we can actually convert the data samples for each task into this instruction tuning template. So this is a data sample from the natural language inference task, where the task is to predict whether this hypothesis entails from the premise. So if it entails, it's yes. If not, it's no. Sometimes you have a sort of what's the word, not applicable label as well. But yeah, just think of it as a binary case in this case. So given this input and output pairs, how do we construct instructions? We can basically say, based on the paragraph above, this one here, paragraph premise here, can we conclude the hypothesis? And we give the options, either yes or no. And the output will be either yes or no, right? Or we can rephrase the instruction and say, read the following and determine the hypothesis. If the hypothesis can be inferred from the premise, Or we can just be more simple and say, can we infer the following by providing this premise and hypothesis. So these are the placeholders where you will insert each different pairs of input data, and you will have, in this case, 4 different ways to populate them. And the reason we have like multiple styles is to cater for the fact that the users during the inference time may ask instructional questions in their own ways. So it's better to have a diverse templates following different kind of styles. And then of course the generalization can happen based within the instructions as well. So it's also the main reason. And people now have been sort of trying to scale up this instruction fine-tuning and consider like this really large number of tasks. So this supernatural instruction data set contains over 1,600 tasks with more than 3 million examples. So, at this point, you should really call this as instruction pre-training than fine-tuning, just because of the sheer scale of the data set. But having said that, researchers at Meta found that quality over quantity, that's what matters. So in their paper, they report that if we manually inspect data samples, instruction data samples, so that we can only retain the high quality ones, and as long as they're diverse enough, as few samples as just 1,000 samples are enough to beat the models that were trained on much larger instruction data sets. So this kind of suggests, this is kind of a good news for small scale research groups or startup companies where you want to fine-tune your language model to your particular domain. Maybe it's the case that you don't need to spend that much to construct a large scale instruction data set. Okay, and then this brings us to this sort of, how should I frame this? Like this concept of general purpose instruction tuned model versus like task specific instruction tuned model. I'll just take some sip. So consider this. So this sort of bullseye diagram is abstract visualization of the task, this learn distribution for specific tasks. And because these models are trained to perform as diverse tasks as possible, the learned spaces could be quite sparse, just because there are so many different types of tasks, as opposed to more task-specific tuned model. So this is a bullseye diagram for the task distribution plot for the text refinement model, instruction tuned model that's refined for text refinement. And here we have similarly, conceptually similar tasks, right? So we can refine the text to be more neutral setting, make it more coherent, simplify it, or paraphrase it. All of these sort of different tasks are kind of related to each other. So the learned distribution will be really dense as opposed to the sparsity here. And the idea here is that as long as we have an unseen task and as long as it is related to the domain of text refinement, the chances are our learned distribution might have already covered this new unseen task, which is about making text more polite. Or in addition, if a new task is a composite task, meaning that it consists of performing several tasks, like making the text more readable, making it more coherent. And if we already learn these kind of separate tasks, we can piggyback from their distributions as well. Okay, so in this paper, this work in collaboration with Grammarly and our lab, so we took existing pre-trained instruction-tuned model, so general purpose instruction-tuned model, and further aligned this model with bunch of tasks that appear that is related to text refinement. So we have grammatical error correction tasks, simplification, coherence, style transfer tasks, and we turn each sample into these prompt templates. So for fluency task, our so our instruction was to fix the grammar, and then we give the input, whatever, right? And to encourage diversity in the instructions, we have a bunch of other types of related instructions here. So it could be like fix grammar in this sentence, make the sentence more fluent, fix errors in this text. Yeah, so each of these instructions are picked from these verbalizers and appended to produce the actual samples for the instruction tuning. And similarly for the other tasks as well. So yeah, that's pretty much it. And the results are very good. So this instruction-tuned model managed to outperform existing domain-specific models. These ones are not previously instruction-tuned. They're just trained on these data sets in a sequence-to-sequence manner. But yeah, when they are instruction-tuned, they achieve much better performance, especially with much fewer number of parameters as well, right? So that's good news. And if you want to try out this model, they're available on Hugging Face, so you can just load them and test them like this. Okay, so now let's talk about how we can evaluate these instruction-tuned models. So the main purpose of instruction tuning is to encourage generalization ability across diverse set of tasks, right? So, evaluation would be exactly that, right? So we can evaluate on unseen or zero-shot tasks where we don't, where no data sets from the task were used during the training. So here we have the natural language inference task, and provided, and even though these NLI tasks data sets are not part of the input, not part of the training, because to infer the relationship between premise and the hypothesis, you gotta have some understanding of the text, right? So reading comprehension is required. Maybe common sense reasoning is also required. So so piggybacking from these learned distributions of the related tasks, we can do some, the models can generate appropriate responses, even though it's unseen. And we call this phenomena as emergent abilities of LLMs. And people have been trying to create a bunch of data sets to test their limits and capabilities. This data set, MMLU, collects a bunch of knowledge from like diverse domains. So it just asks whether LLM knows about this like fact or knowledge. So it's a knowledge-intensive task. And in a more general purpose setting, Big Benchmark incorporates like 200 plus tasks, and they range from traditional NLP tasks like reference resolution, named entity recognition, to more sort of reasoning or behavioral tasks like common sense reasoning, analogical reasoning, causal reasoning, human-like behavior, those kind of stuff. But we can see that the majority of the tasks are fewer in the number of samples. So most of them range from a couple of hundreds to thousands. So it's a relatively small test set. And this is another benchmark that tests whether the generations of the language models exhibits some sort of cognitive bias when they are used as evaluators in replacement of human evaluators. So this is the work that one of our lab members did. So the idea here is that given this instruction data sets, and we just fed it using like different LLMs, we gather the responses, and we do some pairwise testing. So we pair the responses like so, and then we do prompting again, but this time in order to evaluate which one of these two samples or the responses are better. Okay, and we do this evaluation across different LLMs as evaluators here. And we check the result whether the evaluation results show some of these cognitive biases. So we identified 6 different types of cognitive biases. 4 of them are implicit biases, and the other 2 are induced biases. So implicit biases, we don't really try to do anything to steer the behavior of LLMs. We just prompt them while varying some of the settings that we like to see. So for example, for the order bias, this is based on whether the LLM predicts, whether the LLM prefers certain options based on the ordering of their options. So we can first give the candidates system star followed by system square, and then we can try again, but this time by changing the order. So system square followed by system star. And if the LLM is unbiased, it should be able to maintain consistent prediction by either flipping the ordering, right? So if you prefer the star, it should prefer the star as well, even though it's shown in the second to the first one. And then I can just briefly explain the bandwagon effect as well. So for the induced biases, here we are trying to intentionally steer the behavior of LLMs. So try to induce the undesired behaviors, something like the adversarial attack. So similar settings, but in addition, for bandwagon effect, we say that, by the way, 85% people preferred response A, and try to see whether that affects the preference of the LLMs or not. Even though that this might not be the correct answer, right? So we can say like 1 + 1 is like 2, and then 1 + 1 is 3, and then we can just say majority of people preferred 1 + 1 = 3 options, but the LLM will still need to choose the first option, right? So these are the main findings, and the takeaway is that even the GPT-4 models, even like really strong and powerful models, they're shown to have these kind of cognitive biases. Especially they're shown to have this compassion, saliency, and egocentric bias. So egocentric bias is where the model prefers their own response more than the other ones. So when you are using LLMs as in replacement of human evaluators, you should be careful of this kind of stuff. Okay, so that was the instruction tuning part. So do we have any questions? Okay, then I guess we can move on to the next part, which is the augmentation of language models. So what are the weaknesses of language models? One obvious thing would be that because they are trained, they would be bound by the training data of the time, right? So the latest knowledge after the model pre-training is cut off. And also, if you require to utilize sort of your company's internal knowledge or private knowledge base, or even external knowledge base, this is difficult to do so. And also because they're trained with next token prediction task, tasks like symbolic reasoning or deterministic execution of some program codes, mathematical equations, these are all very difficult for language models. And this difficulty are stemmed from their fundamental limitations. So language models, essentially, they're statistical models where we try to cram the knowledge into fixed size weights, fixed size model, right? So in that sense, it's called parametric because it's bound by the size, fixed size of model weights. And of course, the input context is also bounded, right? There's only so much tokens that you can feed into the transform models. And more fundamentally, these language models, as I said, are trained to do well on the next token prediction task. So they doing like symbolic reasoning is not intended by this task. So how do we actually improve upon these weaknesses and limitations? So the recent trend, especially in industry, is to move away from this purely statistical language modeling and try to integrate external components before generating the response. So that the external component provides additional information so that more relevant context is produced. Context here could be the examples that you fit in your prompt. At the cost of more computation, of course, because you need to call additional stuff or conduct additional process. But now you're no longer bound by the fixed size model parameters, right? So in this sense, you can consider it as a non-parametric models, which is good. And you can think of this augmentation in terms of 3 dimensions. Augmentations to improve reasoning capabilities, augmentations to use external tools, and then the augmentation in terms of the act of calling the tool that will have an effect. So reasoning tool and act are sort of 3 dimensions, and they're not necessarily sort of exclusive to each other. Like most of the time, they sort of overlap. But it's a good dimension to have in mind when you read a paper on augmented language models. So this is kind of the conceptual diagram for augmented language models. So now you have this environment where both the tool and your language model here now is termed as agent because the assumption here is that it now has some ability to do the reasoning, has some memory and so on. So we will call it as agent. So it interacts with the environment and the tool also interacts with the environment. So given sort of a prompt or instruction and given the state of the environment, if necessary, the agent will plan the subsequent steps, make a decision, and from this decision, it will physically or programmatically call the tools and execute the tool, and then retrieve the results from the tools, and those will be fed into the memory as well. And based on that results, it will do some planning, decision making, and control again. So this is kind of the process here. So the tools can be like an API interface. It could be just a simple call to the Google search engine. It could be a call to the weather API, whatever. Or it could just be a predefined rule set. You may want to invoke some sort of a rule. Or it could be an interpreter, like a Python interpreter. Or it could be a logical symbolic interpreter. And if you're working with robots, the tools can also be the physical device that you can call upon, like a robotic arms or something like that. Okay. So now let's look at the reasoning, the augmentation techniques regarding the reasoning aspect. So reasoning is, as we know, is the ability to make inferences using evidence and logic. So you can think of common sense reasoning, mathematical reasoning, symbolic reasoning. And oftentimes it involves deductions from inference chains, meaning that you need to solve multiple steps of reasoning to reach the final goal. So the main challenge here is breaking down a complex problem into subproblems like the divide and conquer approach that we learned in algorithmic class. And how to generate solutions for each subproblems and how to aggregate the solutions to arrive at the final answer. And you can sort of elicit this reasoning in LLMs roughly in 3 different ways, like using the prompting techniques. So, whether it's a COT, whether it's few-shot, chain of thought, whatever, or you can just recursively or iteratively call the prompting again and again, or you can do some teaching. So teaching here means you are backpropagating with the gradients. So the learning is involved here. But these 2 models don't require any learnings. And of course, these 3 approaches are not necessarily mutually exclusive. So you can sort of mix and match. We'll see some examples. Okay, so let's take a look at the eliciting reasoning with prompting approaches first. In the previous lectures, I think you have learned about this, zero-shot prompting and chain of thought prompting. And this is in context of doing reasoning, right? So zero-shot prompting means that you're not giving any examples. We're just asking the models to do the task. And funny sort of finding from this paper is that if we ask the language model to do let's think step by step, then oftentimes it produces this COT-like responses. So this is kind of a trick that you can elicit reasoning by just simply adding let's think step by step. Or more recently, this paper talks about this chain of thought decoding. Again, this is nothing more than just decoding the generations. But at the step 1, we take the first top 5 most likely words, and then we continue greedy decoding for each of these 5 tokens. And they found that the language models will generate COT reasonings. And surprisingly, the reasoning chains with the correct answer has the highest confidence scores. So if we do this, and if we just select the chains that has the highest confidence scores, usually you're correct. So yeah, this just kind of shows how we can do chain of thought reasoning with more decodings. Yeah, so that's pretty much the zero-shot way of doing things. And in terms of few-shot promptings, these are mostly related to the COT promptings. So in the original COT promptings, you are either explicitly telling language models how to arrive at the task problem by explicitly saying, you need to do this step first, and then followed by this step and this step. In the form of examples, right? In the form of few-shot prompting, right? So that's what the chain of thought prompting refers to. But you can think of an extension where you can consider multiple chain of thoughts, right? So you can have like several chain of thought reasoning going on, and then at the end you have some sort of way to select the best prompts, maybe by confidence scores or some sort of heuristics. But these chains are not necessarily, these chains are separate from each other. These are independent chains. And recently, the tree of thought prompting, they generalize these multiple COTs further by first delineating the thoughts from the responses. So here, this is thoughts. Or the steps to be computed. And each And each depth of the tree, you are allowed to backtrack to the previous trees, the previous nodes, if the reasoning chain is deemed to be poor or not good enough. So this is kind of, you can just think of this as doing backtracking, implementing backtracking algorithm when you are searching a tree data structure, right? So this is conceptually the same. And yeah, so here you get to explore the intermediate outcomes, intermediate thoughts from the different levels of tree, whereas in previously these are sort of separate. And then these authors, they even generalize this further. Now it's no longer a tree, it's a graph now, because tree is a special case of graph, right? So in the graph of thoughts, they added two things. One, they added this self-refinement case where you can just self-refinement your current thought over and over. And then another is they added this aggregation step where you can now combine multiple thoughts into one thought. Yeah, and the rest is the same. You just traverse these thought branches to arrive at the optimal output. But the obvious drawbacks. Okay, go ahead.
Do you know if there's been any work done to implement this type of graph of thought training within the actual decoder to, like, you know, perform this thinking process before you actually produce an output from the decoder, like within the actual algorithm?
Yeah, that's possible. So there are several decoding strategies, right? The short answer is yes. I think it's possible. So, for example, like, is beam search decoding covered? Yeah. So the beam search decoding, you just maintain the top 5 beams every time, right? So you expand each beam by top 5 candidates. You trim, and then for next iterations, you just maintain the top 5 beams again and again. So that kind of is similar to maybe not multi-COTs, but you can see, as you said, how the decoding strategies can be applied for this task. But the difference here is that the decoding is done at the token level, right? So you can do this at token level for sure. But in this scenario, each of these thoughts are actually like sentences or multiple sentences. Yeah, so that's the only difference.
So has there been work to sort of integrate it into the decoder, or is it primarily just working on the sentence level for this part?
Working on the sentence level. So in the prompt, working on the sentence level. So I don't think it's easy to do this thing at sentence level at the decoding stage. I mean, I don't know, maybe possible, but as far as this is concerned, we're just working at the sentence, multiple sentence level or sentence levels.
Okay.
Yeah. So here, what's decoded is the generation of these sentences. So that can be considered as one decoding step, which is done by the prompting. So that's the different granularity there. Okay, cool. So another sort of paradigm that's been widely popular is still future prompting, of course. But you're sort of now trying to incorporate this notion of programs into their response. So this React prompting is really, really popular and known to work well. It's nothing more than composing the instructions in this manner. So we can have an instruction here, like solve a question answering task, interleaving thought, action, and observation steps. So in the original React paper, they have this notion of thought, action, and observation. So thought is just an internal reflection of the LLM, like based on the current outputs and previous outputs, what should the LLM do next? So it's kind of like thinking out loud stage. But in this instruction sort of setting, we just tell what the thoughts are. The thought can reason about current situation. And then depending on the number of tools we have at disposal, those can be the actions, right? So if we have a search engine API, we can just name it as search tool. A lookup tool, which is just looking up based on the keyword. And then the finish tool, which is just a dummy tool that lets you know that the reasoning is finished. So you can think of, So you can think of this as an overall instruction for doing React prompting, and then followed by this overall instructions, you have these examples conforming to this format, right? So a possible example would be like this. So the thought here, I think the task was finding what the Apple remote was previously designed to interact with, or something weird like that. And given that task, the language model will sort of reflect on the task and say, oh, I need to search Apple remote and find the program it was originally designed to interact with. And from this, it can infer to use the search tool like this. And then at this stage, it will explicitly call the search engine, and the retrieved results from the search engine will be the result of the observation one. And this is fed to the current context of the language model, and then it iteratively thinks again based on these results. So now it thinks that it needs to search front row for some reason. So it tried to search it, maybe through the Wikipedia API, but then it couldn't find it. It said, but the similar entries were like search front row software. And based on this result, the language model correctly infers that it needs to search front row software in the parentheses, and then the result is returned. And from this result, the language model correctly identifies that the answer is keyboard function keys. And then it just, it calls this sort of dummy finish action to let the user know that the reasoning is finished. So following this overall instruction, we append this kind of examples at the end, like a couple of examples. And then we append the real inference task that we want the models to solve. So that's what React prompting is. Any questions? Okay, pretty simple. So at the end, this is all a variants of few-shot learning, right? So we're just giving examples. It's just that the way we organize the examples are in this kind of format. Okay, and this paper does the same thing, but tries to add more structure to it. So in the React paper, our sort of response were like kind of free form, right? The thought was free form, the observation and the action is kind of free form. But this paper tries to add like use a structured query language to add more structure to construct these examples. So here now we can see these examples are more structured. Excuse me. So we have the task, input text, question, followed by the tools that we need to use, the arguments that this tool accepts, and then followed by more sort of these reserved special keywords. So the idea is that using a custom parser, we can now parse the outputs of the language models and end up with structured results, as opposed to having it in a free-form text. Okay, so that's the main idea here. Yeah. we can take a look at this next slide. So again, it follows the fuchsia prompting approach, but this time they have these examples stored in this thing called task library. So they have a bunch of different tasks, code operations, COT, reasoning, search, arithmetic, whatever. And then given this new task and the input, they first search this task library and retrieves the most relevant task from the task library. And the task here is computing some sort of force, like a physics question. And it ended up retrieving the task of arithmetic computation and the anachronism task as a relevant task. And these will be the few shot examples of the prompts. And the language model is expected to follow this grammar by looking at these examples, which is pretty interesting in my opinion. And if it's possible that the language model may not adhere to this grammar, and then they have this routine where they check whether their parse tree is complete, and they repeat the process until the grammar is complete. The response adheres to the grammars. Yeah. So for this task, for this input, Hector blah blah blah. Given this input and these references, examples, the language model predicts that it needs to search the formula for the computing the horizontal component of tension forces. It retrieves the formula, and then now it reasons that it needs to generate code to compute this formula. So the code is generated, and now it reasons that it needs to execute this code. So the code is executed, and the answer is returned with this EOQ symbol, signifying the finish of the reasoning. So one of the additional benefit of this approach is that now humans can take a look at the reasoning step, and they can sort of change or correct these reasoning steps, right? Because and the correction is deterministically known to work because this is now in this sort of structured format. So as opposed to correcting the behavior language model in free-form language, this is more sort of constrained, but has a higher probability of delivering the results. Yeah, so you can incorporate human feedback in the loop if needed. Yeah, so that's pretty much it about this paper. So this was so far how to elicit reasoning capabilities in language model through prompting. And now let's take a look at how we can call tools and act upon it. Okay, just 1 hour's passed. Okay, cool. So now that we have some ways to do reasoning, we need some ways to incorporate external knowledge, right? So that's where the tools come in. And this integration of tools is often done by having these special tokens in our language model's vocabulary. And whenever this token is encountered, we will call the corresponding tools. And this tool can do like exact computation. It can be tools like Prolog can be used to do some like logical inferencing. And of course, we can call other search engines to do some information retrieval tasks. So tools can range from simply calling another LLM or another tool like programs like Python interpreter, or it could be correspond to querying vector databases, knowledge graphs, or search engines. And the second is often referred to as information retrieval in the NLP domain. So the very first paper that did this used the Google search engine. So given a question, like a prompt, they just called Google search engine and retrieved the top 20 results. And then they filtered these returned results by TF-IDF metrics. But of course, you can use another language model to do some preference ranking. And then they just use the highly rated ones as part of their input prompt. So only the most relevant paragraph is used in the prompt to produce the answer. But so in this paper, they just used this calling of Google Search Engine API as a single tool. And so in general, conceptually, when you do this retrieval augmented generation, these are sort of the conceptual figure here. So if you ignore the first two steps, user query goes in, language model projects the output. So these are like just a standard way we use language models. But now the retrieval process works by first extracting the relevant samples and documents from the user query, either from the databases or from the search engine, and somehow combine those results to your original query, and that becomes your new augmented input. So the idea is that you the idea is to organize inputs by fetching most relevant examples that will likely improve the answer of the language model. And so this is not exactly retrieval, but you can think of this internal retrieval here, where you are querying your own language model. So the language model queries itself. So prior to generating answers to the question, these authors, they ask the language model to generate some knowledge about the questions, and then use that generated knowledge as part of their input sequence. And it has shown to improve the performance. But this is not exactly non-parametric setting, right? Because you're still using your own weights. And another similar paper, so this is to do with the iterative text refinement task. So, and this is also ties back with the recursively prompting language models to do reasoning. So here, it just iteratively prompts the language model to refine the text. So given this text, the language model has determined to do remove some incorrect information, and the edit is the following outcome, and then given this results, it will prompt itself again, and then it now decides to do additional information about the career of this person, and then again and again. So this is repeated until there is no further update, or until the maximum step of iteration is reached. And you can augment the language models with the Python interpreter, as we have talked about. So this is the early paper, right? So what they do is, given this kind of numeric questions or algorithmic questions, rather than generating COT reasoning, we ask the model to generate Python code for that problem. And the chances are, if it's a well-known problem, the language model might have already been trained on it. So the chances of it generating working code is higher than just doing everything from scratch from the COT reasoning. And once the code is generated, we can just call the Python interpreter to run the code and arrive at the answer. And you can see how all these kind of different tools can be fit into the React paradigm or the art prompting paradigm we have just seen in the previous slides. And in the previous slides, we have looked at approaches where you don't need to fine-tune your language models. But here, for some cases, you may want to fine-tune on these specific tools. If you know what kind of tools you're using, maybe if you want to service this language model to the public, you want to be really sure that your model is delivering these kind of reasonings in a more sort of structured manner. Because if you do prompting, there's always some sort of a randomness involved, right? But if you actually embed these tool calls in the training data and just fine tune on it, it's in some sense it's more robust, right? But the downside is that you're bound by the tools that have been used in the training data, so it's difficult to bring in new tools at the later stages. But anyway, the idea here is to encode within the text, natural language text, this usage of tools. So so for example here, how hot will it get in New York City today? And then we can add this weather tool, calling the weather API, look up region equals New York City, and then we can attach the results here. So whenever you are generating during the inference time, this kind of appropriate tool token will pop up because it's been fine-tuned on it. And when these kind of tokens pop up, you will call the external weather API and use the results as part of the generation. And this tool format paper is also quite related. But rather than manually adding this or heuristically adding this tool, it uses language models to specify which kind of tools to be added at which place. So it uses language models to do some annotations by itself. So these are like possible annotations here. And then, of course, not all of these annotations are useful. So they have a filtering stage where they compare whether the output of the tools is helpful in predicting the next token of the actual generation. So if it did help, then they will retain the tool calling. If not, they will just remove that from the annotation. And then same as before, they just fine-tune on this usage, explicit usage of tools in their texts. Okay, so now I would like to talk briefly about constraining the generation of your language model. So I think this could be useful in some of your group projects. So you might have faced with this situation where you want the language model to output either yes or no, but sometimes it outputs something totally random, like maybe or something, and then you don't really want that, right? So you can use this kind of constraint generation tool like Guidance from Microsoft AI, and it allows you to constrain the generation with regular expressions, or if you want to be really involved, you can define your own context-free grammars as well. And then it has built-in capabilities to do like conditional and for loops and so on. So, this is a kind of basic usage here. So the prompt, and then if you call generation function, gen and the max token 10, it will generate up to 10 tokens. And then you can also say when to stop. So if it generated with my space, if it generated space, it will stop. And then at the end, you want the model to conclude with either new line, period, or exclamation mark. This kind of constraints can be added. And also, this is quite useful. So similar to the yes or no choice question, here you are constraining language model to output either one of these three colors, like red, blue, or green. So what it does is it will look at the probabilities of these three tokens, and it will just choose the ones that has the highest one. So I like the color red. It's generated. You can specify regular expressions. So given this question, like Luke has 10 balls, blah, 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 how many does he have left? And if you want the answers to be Arabic numbers, then you can just use these regular expressions like this. So this means that digits, one or more digits are accepted. So now it generates 7 instead of 7 in English words. So take a look at this guidance library. It's very, very useful. Yeah, and you can integrate tools as well, so pretty easily. So let's say you have these kind of 4 tools, which are just Python methods: add, subtract, multiply, divide, and then you just add this decorator here, add guidance. And when you generate, you can just mention that, oh, you will be using these 4 tools. And if you happen to have this name of the tool in the prompt, it will call this tool and replace with whatever result it will produce. So yeah, again, this is very, very useful. So before concluding, I just want to briefly introduce some works that uses LLM as agents. So, now LLMs are capable of doing some kind of reasoning, and they have some memory, and they have some access to external tools. So you can think of them as an agent, right? So some works, they try to use LLM as an autonomous agent. So as I said, they are tasked with realistic and high-level goals, like gather and summarize recent papers published in this month and create a GitHub repository using the summarization, whatever. So as you can see, there are multiple steps to be met, right? And LLMs can now, to some extent, handle these kind of goals by breaking down into sub-goals and validating whether their intermediate results are correct or not. Or they can also work as social agents. As I said, they can simulate human interaction. And then, people who are interested in AI ethics or interested in social science can ask these kind of questions, right? Or LLM interactions aligned with human values. You can observe how LLMs interact with each other. And, are they aligned with what we want them to behave? Or, we can look at through this interaction whether they can replace human crowd workers or not. So this first work is regarding the LLM as autonomous agent. So there are several works on this aspect, but this paper called Web Arena creates this environment, a web environment, where they defined multiple high-level tasks in domains like e-commerce, social forums, software development, and content management. And they have this GPT-4 based agent that tries to do this kind of task, and they represent the observations from the tools in these 3 different settings. Left is the image, the screenshot, so the LLM sees the image of the observation. In the middle, they have the HTML DOM tree, and on the right, they have this sort of their own version of accessibility tree. And they found that the accessibility tree representation of observation results works best. But as you can see here, that the success rate for this complex task is only 14%, even with the GPT-4, whereas human performance is 78%. Quite surprised that this is actually not greater than 78. But yeah, there's a big gap between the human and the GPT results. So you can take a look at this link, and it will show you some demos of these LLMs performing these kind of tasks. Okay, and next we have the LLM as social agent. So here, they create this sandbox game-like environment, something like Sims, and then they initialize LLMs with different personas, and these agents will follow some standard routine, like they wake up, they cook breakfast, they head to work, and when they are going, to the workplace or going to the park, when they notice each other, they will converse with each other. They will memorize what kind of conversation they had with each other, and then they will remember and reflect upon the past events, and also they are able to plan the next days. So in the paper, I think one of the scenario was hosting like a birthday party or something. So they just give this scenario and just observed how these LLMs as agents interact with each other to achieve this goal. Yeah, so if you're interested, this is pretty cool too. Okay, so to conclude, yeah, so a lot of stuff we talked about today. So on alignment, we talked about capability and alignment of language models. Instruction tuning works very good, really effective, seems to be effective in bridging the gap between capability and alignments. New benchmark has been proposed, even to this day, to really test the model's capability. And on augmentation, yeah, the reasoning abilities and the fact that it can incorporate various tools and knowledge bases, that resulted in great performance in general. So the main task here is to how do we more cleverly decide which tool to use and what relevant external knowledge to fetch. So these are sort of, can be task dependent and something to consider in your project as well. Yeah, so I guess that's it.
Let's give it a couple.